Hello everyone, welcome to this meeting. This should be the second meeting on estimators, asymptotic theory, and random variable convergence. And as you know, it's part of this half a year series of statistics lectures. If you have not signed up yet for the different notes and quizzes and homework, there's a sign up form right here. So if you just submit this form, you should receive the information about the materials by email. And that's true even if you are watching this on YouTube. The last time we were talking about estimators, we defined estimators. I provided a simple example of an estimator. This was really considering one particular random variable y that had some kind of distribution, and we were interested in estimating the mean of the distribution. We said that we would have n observations in our data set, and the individual observations in the data set would be themselves random variables that would take certain values. And we discussed an estimator that was basically just taking the sample mean of these individual observations. We talked about its properties and so on. Then we went on to define estimators in general. We said that we would represent our data by some capital X in here. The possible values of X would be this little x, that would be a concrete data set that may be on your computer. And we would have some parameters in the model, and we would be interested in estimating some particular parameter theta. It could be a vector, but it can also be a scalar for sure. Then an estimator of theta would be this theta hat. And we said that this by itself is a random variable. It's going to depend on the outcome, if you like, on the state of the world, and so on. Then we defined some properties for that. We defined the error of the estimator, mean squared error, mean absolute error, sampling deviation, actually a lot of different things. We talked about the variance of the estimator. And importantly, we would define a bias of the estimator. So that would be the expected value of the estimator minus the true value of the estimator, the true value of the parameter. And the estimator would be unbiased if the bias is just equal to 0. It will be biased if the bias is non-zero. We also talked about a consistent estimator, and we said that really a consistent estimator is really a sequence of estimators. The sequence of estimators is going to depend on this little n. The little n is 1, 2, 3, 4, and so on, all the way to infinity. And a consistent estimator will satisfy this particular condition specifically. If this theta hat n is a consistent estimator, then as n goes to infinity, it will converge in probability to the true value of theta. And then we went on to actually discuss these different concepts of convergence. We discussed convergence in probability and convergence in distribution. But as for this part, do people have questions? Was this all clear the last time? I'm definitely happy to answer if anything was unclear. And as for convergence of random variables, that's something that we will need to continue with right now. I'm going to remind you here of convergence in probability and of convergence in distribution. I should also remind you that when we talk about these different convergence concepts, we are actually using in these notes xn as a member of the sequence that's supposed to converge somewhere. So xn is not the data for us here. In the context of estimators, this xn could be an estimator that will or will not converge to some particular true value of some parameter. And as for convergence in probability, we had this particular definition for random scalars. It was a little bit complicated, so we basically had some tolerance level epsilon here. And if we want to say that the sequence xn converges to some random variable x, it has to satisfy this kind of condition for any positive value of epsilon. And yeah, what was the condition? Basically the distance between xn and x. If you think about this distance between xn and x, and you think about the probability that this distance is greater than the tolerance level epsilon, then this probability actually has to converge to 0 as n goes to infinity. So we had this limiting condition in here. And I had some visualization for that. Yeah, the picture was kind of like that. In the picture, we would have the value of x. So x, that would be these like circular dots or circular points. Then we had xn, these were the little squares. The lines between the square dot, square point, and the circular point. That distance that was like this xn minus x in absolute value. And the color indicated whether or not this was greater than epsilon. So specifically, I used the red color in here whenever the difference between xn and x in absolute value was greater than the tolerance level, and blue if it was smaller or equal to that particular value. And the statement of convergence in probability was that the probability of the red color here has to go to 0 as you move right in this visualization. So as n increases, we would start here with n equal to 1, then n equal to 2, and so on. We would increase n as we go to the right. So this was the concept of convergence in probability, at least for scalars. For vectors, we would replace the absolute value with a distance measure. As for this part, was this clear the last time? If you have any questions, I'm happy to clarify. And then we had another concept of convergence that we defined the last time. It was convergence in distribution. And the idea there basically was that the CDFs of the CDFs of the members of the sequence should converge to the CDF of the limiting random variable capital X. And we would require that whenever the CDF of the random variable capital X was continuous. So if you have jumps in the CDF of X, you don't need to impose that condition there. And in writing, the condition looked something like that, right? Well, we would have the sequence of random variables xn, and we would have the corresponding CDFs fn. We would have the random variable capital X to which we want to converge. This would have a CDF f and a distribution dx. And the requirement would be that the sequence of the CDFs evaluated at little x needs to converge as n goes to infinity to the correct value. So specifically f of little x. And this kind of requirement was only when x was at a point where f of x was continuous. And this was the notation for that. The technical definition was a little bit more complicated for random vectors. So this was our definition, but probably I don't need to remind you of that. It's a little bit technical. So as for this part, was this also clear? I would like to make sure that everyone understands this before we move forward, because we have two more concepts of convergence to define, and then we should actually talk about the different relationships between the different notions of convergence. So if you missed something here, then you will also miss the discussion about the relationships between the different notions of convergence. All right, let me check. Okay, looks like it's clear. Great. Yeah, so thanks for the feedback. And let me see. A question. What is the measure that we use when we talk about how closely we are converging to a distribution? So I think you are talking here about the convergence in distribution. And here, we basically impose the condition just on the functions, right? So we basically take these random variables xn and x, and then we look up the corresponding CDFs, fn and f. And at that moment, we basically forget about the random variables and we only work with functions. So at this moment, we are just working with these CDFs. And then we consider the different points little x where f of x is continuous. And for those, we impose this condition. And if you think about it, this fn is a function of little x. If you evaluate it at little x, it's a real number. So at that moment, you have a sequence of real numbers, and you are talking about this, the limit of the sequence of real numbers, and you require that it's equal to this real number that's on the right-hand side. So at that moment, you don't really need to think about the random variables anymore. It is really just a statement about the CDFs. And yeah, if you were actually talking about this slightly more complicated definition for random vectors that involve these probabilities in here, then yeah, these probabilities were basically taken considering some underlying probability space and considering some underlying probability measure. And there will be just one probability measure that we are working with altogether. And then using this probability measure, we define all of the different random variables. And after that, we would talk about probabilities like this. So this kind of probability would correspond to the distribution of the random variable xn, and this kind of probability would correspond to the distribution of capital X. And yeah, so since I brought this up here, yeah, let me say that in the vector case, this condition is only required if this capital B is a continuity set of this capital X. So maybe you were asking about this particular thing, and yeah, then we would be actually referring back to some original probability measure that we have on our sample space. Okay, so thanks for the question, but yeah, does anyone have any follow-up question or any other comment? Then yeah, let's go to new notions of convergence that we haven't talked about yet. And yeah, things can get confusing because there are just so many different ways that you can think about convergence of random variables. And yeah, follow-up question. I mean, f of x is not a scalar, right? It's a distribution. So what is the measure of closeness? Right, so here I want to emphasize that the capital F evaluated at a certain point, little x, it is a real number at that point. So just to be clear, let me jump back here. So we start with some random variable xn, and yeah, it's a random variable. Then we look up the CDF, fn, and that one is just a function. It takes the different possible values of x as argument, and then it will have some functional values that are real numbers somewhere between 0 and 1. So if we take this CDF, the cumulative distribution function, and evaluate it at any x, then it is just a number. It is just a real number between 0 and 1. And you can apply the usual notions of convergence to this. Like yeah, you can take the kind of limits that you are used to in the context of calculus. So there's no problem with that, actually. Okay, great. Yes. So looks like this is clear. Awesome. So any more questions? If not, let's get to the other two notions of convergence. And yeah, by the way, why am I introducing all of these? It looks like too much material. Looks like too many different concepts. The reason is that if you open a statistics paper and it has in there some kind of theorem that has to do with convergence of random variables, then it will also specify which mode of convergence that theorem uses, or which mode of convergence the theorem applies to. And then you may need to be able to interpret whatever the theorem says. So yeah, let's get there. A lot of the theorems would contain this almost sure convergence. So let's try to understand that right now. And yeah, I'm going to read the theorem. I have some visualization here, so I would like to show that to you as well. But yeah, let's first... sorry, I said theorem, I mean definition. Let's read the definition. Let's try to understand the notation, and then let's take a look at some visualization. In some sense, this almost sure convergence is maybe one of the easiest concepts of convergence to define. Yeah, why is that? Because it's basically convergence that considers individual outcomes. So as you know, we were using this little omega to denote different outcomes. You can think of the outcome as the state of the world. And then the actual random variable was a function of the outcome. So if you have the sequence of random variables xn, you can evaluate it in one particular state of the world, so for one particular outcome. And at that moment, this xn is going to become a real number. Or if you have a vector, so if this was a scalar, it's going to be just a scalar real number. If this was a vector, then you would get a vector of real numbers. And at that moment, you would just go ahead and consider the limit. So here you have a limit of a sequence, and you are going to require that the limit of this sequence is actually the capital X evaluated at omega. So it is our candidate random variable that was supposed to be the limit to which xn converges. And yeah, we consider here capital X in the state of the world corresponding to this little omega. So we would be applying conditions like this, but we are actually not going to apply this condition or require this condition for any possible outcome, any possible state of the world. We can allow for some exceptions as long as these exceptions have a probability 0. Or stated differently, we will think about all of the different outcomes, omega, for which this condition is satisfied. Then we will think about its probability measure, and we require that that probability measure is equal to 1. In other words, there should be 100% chance that for for your random omega in here, this limit condition is satisfied. So if with 100% certainty this condition is satisfied, you will say that the sequence xn converges almost surely to capital X. And yeah, you see here AS above the arrow, so AS stands for almost sure. Now it can be that for some of the omega this condition is not satisfied, but the set of all of those omegas for which this is not satisfied has to have probability measure 0. So that's just reading the definition here. I should also show you a picture. And yeah, could you please explain with an example? I did not fully understand. Right, so let me switch to the visualization first, and then you can tell me if that helps or not. So yeah, the relevant visualization I have here for the almost sure convergence is this one. You can zoom this a bit. And yeah, what do you see here? So I will be able to change here the total number of members of the sequence that you see. So we will have some sequence represented by the blue dots. And this sequence is supposed to converge somewhere. And then, yeah, what are the different elements of the visualization? So this black line in here, that's actually an x-axis, like sorry, horizontal axis. And then we would be measuring things in the vertical direction. Then the green dots, they represent the value of capital X. That's the random variable to which xn should converge. And yeah, you just see one value, right? It's because I'm considering just one possible state of the world here. Yeah, I can change the state of the world, and yeah, you will get different pictures like this. And as you see, the value of the value of capital X is changing in here. Now, what about the blue markers in here? So they correspond to the different x's. Specifically, in here, this would be the value of x1, the value of x2, x3, and so on and so on. And it is evaluated for one possible, well, for one given outcome in here, right? And the statement that we had here, the technical statement with the limiting condition, really was a statement about the sequence of xn's for one given outcome, for one given state of the world. So that corresponds to one picture, like here. And then, yeah, we would basically consider this sequence, this value, this value, this value. And yeah, we keep increasing n. And we would take this sequence of real numbers and we would ask for its limit. And yeah, here the condition, this limiting condition said that the limit of xn for the outcome omega was supposed to be equal to x evaluated omega. In other words, the blue sequence here is supposed to converge to the green value that you see. If that's satisfied, then yeah, we satisfy this technical condition for the convergence, that is the almost sure convergence. And yeah, kind of the point was that the limiting condition was supposed to be satisfied with 100% probability. So if I change the state of the world somehow, there should be a 0% chance that this limiting condition would be violated. Yeah, I kind of wonder, so does this help, or should I explain this better? The name almost surely is a bit confusing to me. What is the thing that we are unsure of here that is perhaps probabilistic? And well, yeah, you can think of the following, right? So you can consider the different outcomes, the different states of the world. And for each outcome, you can ask, so is this limiting condition satisfied or not? And you may have some outcomes where it's satisfied. You may have some other outcomes where it's not satisfied. And then we could ask for the probabilities of these two sets. The claim is that we require that the set of omegas for which this is satisfied has 100% probability. And then if you have some omegas for which this is not satisfied, altogether these omegas should form a set that has measure 0. So probability 0, actually. And Yeah, the question, even when n tends to infinity, and so here I should be actually clear. The condition is on the limit. So you have one specific omega that you think at a given time, and then you consider this whole sequence of xn's. So you would see the whole sequence of the blue numbers in here. You would find out what is the limit of that. And if the limit is the correct limit, you will say that the condition is satisfied for this particular omega. That is, yeah, we are not imposing here actually any condition on some finite n. The condition is only on the limit when n goes to infinity. All right, yeah, hopefully this is a little bit clearer, but if you have any doubt, please let me know. So really, this is a condition where we think about the individual outcomes separately. And then, yeah, the fourth condition, the fourth notion of convergence, we will have convergence in rth mean. Yeah, I have some visualization like this. Yeah, maybe I should switch to that one. So the visualization for the convergence in rth mean is as follows. So we again have here some kind of green dots. They represent the value of capital X. Then we have these blue squares. They represent the values of xn. But this time we are going to be focusing on something else. We are going to think about the discrepancy between x and xn. So yeah, it would be kind of this distance here, this distance here, this distance here. Yeah, you have the distances indicated here by the red lines. And then we will consider some power of this length of the red line, and we will consider the expected value of that. And then we will require that this expected value is going to go to 0. Maybe at this moment I should really go to the I should go to the technical definition, because yeah, probably doesn't make sense at this very moment. Yeah, as for the definition of convergence in rth mean, first, let me say that the little r, it actually refers to some power that we have in some definition in here. Then, we would like to say what it means for a sequence of random variables xn to converge in rth mean to some random variable capital X. And this little r, that's going to be some number that you choose, but it has to be a number that is greater or equal to 1. And we are going to assume that if you take the absolute value of xn and you raise it to the power of r, the expected value of that exists. And similarly, we will make the similar assumption for capital X. Finally, we impose this particular condition. So we think about the distance between xn and x. That would be the absolute value that you see here. We raise it to the power of little r, and then we take the expected value. Here we take expectation over the different states of the world, if you like. So once you have the expectation, you consider the limit. So the limit as n goes to infinity, and this limit has to be equal to 0. So in the visualization, it's a little bit hard for me to indicate the expected value of all of this, but really think about this particular picture position by position. At each position, think about the length of the red line, raise the length to the power of little r, and then take an expectation. And the expectation would correspond to considering different outcomes, like different states of the world that you see here. Once you have that expectation, the claim is that as n goes to infinity, this expectation converges to 0. And of course, the expectation itself is going to be some real number in here. Therefore, we can just think about limits in the usual way. And the limits of the sequence of real numbers, this limit is supposed to be equal to 0 for us to say that something converged in distribution. And as for the notation, you would again use an arrow, and you would write the value of little r above that arrow to distinguish it from the other notions of convergence. So that's the fourth notion of convergence, the last one that I wanted to introduce here. But if you have questions, please let me know. Yeah, was this visualization clear, or is it everything all right? Okay, now let's get to the different relationships between these concepts. Okay, a question, does this type of convergence have a special significance? Well, I guess, like, depending on the problem that you are trying to solve, different notions of convergence will be more relevant or less relevant. I should say that this notion of convergence in arithmean is actually fairly strong. So it's going to be implying also the convergence in probability and convergence in distribution. But yeah, so let's think about the different relationships between the convergence types. Yeah, by the way, when we start talking about regressions, you will also see these different convergence types, like convergence in probability and stuff like that. Yeah, now that I think about it, maybe before we get to the relationships between the convergence types, I may want to provide one more definition in here. The notion of asymptotic distribution. And specifically, if we have a sequence of random variables x1, x2, x3, and so on, let's say that the sequence converges in distribution to some particular distribution, capital D. Then we will say that capital D is the asymptotic distribution of the sequence. So if you hear the notion of asymptotic distribution, it is really the distribution to which this sequence of random variables converges. So relatively simple definition here, but now let's get to the complicated stuff, relationships between the different convergence types. You may want to understand these in order to be able to understand the significance of different theorems in statistics and so on. And I just indicated here some of the relationships, not all of them, but I'm going to read these out loud. So you may want to start here with almost sure convergence. Let's say that we have a sequence of random variables that converges almost surely to this random variable x. Then, as a consequence, you also have convergence in probability. So xn is going to converge in probability to x. And in turn, this implies also convergence in distribution, or to say it properly, if your sequence converges in probability to capital X, it also converges in distribution. So we have these two implications in here. That is, the almost sure convergence is actually pretty strong. As for the convergence in arithmean, it's also pretty strong. So if you have xn converging to capital X for some little r, where the little r is greater or equal to 1, then it also implies convergence in probability. And that in turn implies convergence in distribution. Actually one more relationship in here. Let's say that you have convergence in arithmean where r is fairly big, And then you have another r, let's call it r tilde, that is a little bit smaller. Then the convergence in the higher mean for larger r is going to imply convergence in this lower mean in the case of this r tilde. So these are some pretty important relationships. You don't have to remember all of them, but you should be aware that these relationships exist. And yeah, as for counterexamples, I just wanted to highlight one of them here, which is convergence in distribution not implying convergence in probability. That's actually pretty important. It's pretty important to get some intuitive picture of what's going on with convergence in distribution. So the notion of convergence in distribution is actually pretty weak. Yeah, if something converges in distribution, it has relatively weak implications. Let's try to understand intuitively why that is. So here's a simple example where you would have a sequence that is converging in distribution to a particular limit, but it's not converging in probability to that particular limit. And our random variable here is actually going to be pretty simple. Let's say we have some random variable called capital V, and it basically just corresponds to a coin flip. So we will have a 50% chance of getting number 1 and 50% chance of getting number -1. And as for the sequences, why don't we choose them in this particular way? We will say that the limiting random variable is capital V in here, and the sequence is going to be minus V. That is, for any n in here, the sequence member is going to be minus V. Then we can actually claim pretty straightforwardly that xn converges in distribution to x, but it does not converge in probability to x. In fact, yeah, in this particular case, xn converges in probability to minus x, which is quite different. And yeah, you may wonder why that is. I have some additional clarification in here. Yeah, if we define capital X in this particular way, minus V, then it has a distribution that places 50% chance on x equal to 1 and 50% chance on x equal to -1, right? If you think about xn, the same is true, right? We have 50% chance of xn equal to -1, 50% chance of xn plus 1. That is, the two distributions are identical. Xn is distributed in exactly the same way as x, and for that reason, xn converges in distribution to capital X in here. So that's like a first part of the claim. And yeah, the second part of the claim is that this xn does not converge in probability to capital X. And yeah, so why is that? So if we have x taking the value of +1, then xn is going to take the value of -1 and vice versa. If x is equal to -1, then xn is +1. That is, these two random variables actually always differ by 2. They don't actually get any closer as n goes to infinity. That is kind of the only thing that these two random variables share is the distribution. But the values, they're actually far apart for any n in here. And in fact, for any state of the world. The difference between xn and x is always equal to 2. So that's one counterexample that you should keep in mind. And yeah, it kind of illustrates also that maybe just calling this convergence to a random variable is a little bit misleading. So we say that xn converges in distribution to capital X, even though it actually doesn't get even close to capital X. It's just the distributions that are the same. Yeah, is this counterexample clear here? So you need to be careful about this, and yeah, if you have a theorem that guarantees convergence in distribution, and if you think that you can actually, if you think that this actually implies convergence in probability, that's a big mistake, and you should avoid that. All right, yeah, looks like things are clear here. Great. Then some more things about the convergence of these different distributions, or like a convergence of the different random variables. So I just said that a convergence in distribution does not imply convergence in probability. But the thing is, if the limiting random variable is just a constant, then an implication like that actually is true. So if this capital X is just a constant C, so it always takes the value of C, then if xn converges to this C in distribution, then you can also show that it converges to this C in probability. So that's something pretty useful. And yeah, you can also think about sums of random variables. Yeah, what would be the different theorems, kind of the baseline theorems? If xn converges almost surely to x and yn converges almost surely to y, then the sum is almost surely going to converge to the corresponding sum x plus y. Similarly, for convergence in rth mean, if xn converges to x and yn converges to y in rth mean, then also this sum xn plus yn is going to converge to the sum x plus y. And yeah, you would have the exact same statement also for convergence in probability. So if you have two sequences that converge in probability, then the sum of the sequence members is going to converge in probability to the sum of the two limits x plus y. But here things get tricky when you start thinking about the convergence in distribution. So here, this will actually not be true. This kind of theorem will not be true for convergence in distribution. If xn converges to x and yn converges to y, both in distribution, then not necessarily xn plus yn converges to x plus y. And I have some explanation of that. It's kind of related to the counterexample that we just discussed. And here, I should be able to quickly convince you that this is a theorem that is incorrect, right? That is, we do not have this kind of implication. Why? Well, let's set up the random variables in here. Let's think about the coin flip variable again. That's capital V. That will have 50% chance of +1 and 50% chance of -1. And let's define the different x's and y's in this particular way. So x is v, y is v, xn is v, and yn, importantly, is -v. So if you think about it, if you sum the limits x and y, then the value is going to be 2 times v. Whereas if you sum the sequence members, xn plus yn, they will actually cancel each other, and yeah, the sum is equal to 0. And yeah, then you get actually two very different distributions, right? So this one will be like the distribution of 2 times v, whereas here you have 100% chance of just the value of 0. So we have a discrepancy here between the sum of the two limits and the limit of the sum. Yeah, is this counterexample also clear, or any questions about that? All right, yeah, so if this is fine, let me move on to other things, kind of very important theorems. Not doing very well on time, but hopefully you don't mind staying a bit longer. Yeah, there's the law of large numbers and the center limit theorem. So these are very, very important concepts, very, very important theorems. Let's look at them. The law of large numbers. Yeah, what is it? We are going to have actually two different versions of this law of large numbers, but just quickly, the law of large numbers roughly says that if you have a data set that is very, very big, then the sample averages are going to basically correspond to the expected value of the underlying distribution. I guess I should actually read the statements of the theorems, but yeah, in this visualization that I'm showing you here, you will have each dot representing one sample average for different sample sizes. I'm changing the sample size here along the horizontal axis. And yeah, you see as the sample size becomes bigger and bigger, the sample average here becomes more and more certain and approaches a particular value. So here I was taking actually a distribution that has mean 0, so this actually nicely converges to 0. As for the specific theorems, you would have like two main versions of the law of large numbers. Let's first take a look at the weak law of large numbers. It would be a statement about a sequence of random variables. This will be x1, x2, x3, and so on. And these random variables are going to be independent and identically distributed, so they are going to be IID. You can think of them as different draws from one underlying distribution. And yeah, maybe this is your first observation, second observation, third observation. And all of these different observations are going to be independent. And yeah, all of the distributions are drawn from the same, all of the observations are drawn from the same underlying distribution. As for the underlying distribution, it's going to have some expectation, some mean, and we are going to assume that then that expectation or mean is a finite number. We are going to denote that finite number mu in here. You can also write that it's expected value of x1. It doesn't actually matter that I wrote x1 in here. I could have written x2 or x3 because we are assuming these are IID. And then finally, we would be taking these sample averages for increasing sample sizes. That is, we are going to take the first n members of this sequence. We are going to sum up the values of those observations, and we are going to divide that by little n. So really here we are taking the sample average of the different x's. These are going to be random variables, right? So x1, x2, x3, these are all random variables. Therefore, this sample average is also a random variable. It will have some distribution, and the claim of this theorem is that this random variable is going to converge in distribution to just one specific value. It's going to converge to the underlying expected value. That is, here we are converging to a distribution that corresponds to getting the specific value mu with 100% chance. Yeah, so you could say that the sample averages for large enough and approximate the expected value. And yeah, I said that in terms of convergence in distribution, the same is actually true for convergence in probability. So the sample averages are going to converge in probability to this specific value mu. By writing this, I basically mean a random variable that with 100% chance takes the value of mu. And why is that? Yeah, we just talked about the different relationships between the different notions of convergence. And we said that convergence in distribution, when we are converging to a constant, does imply convergence in probability to that particular constant. So that's why we can actually make both statements in here. So that's the weak law of large numbers. Roughly speaking, sample averages well approximate the underlying expected values. So this is the weak version. There's a strong version as well that has stronger assumptions. It's actually pretty similar, but yeah, let's take a look at that. The strong law of large numbers. Again, we are going to have this sequence. These variables are going to be IID. We are again going to have some finite expectation mu, but we are going to make one more assumption in here. Specifically, we are going to assume that the second row moment exists. So the expected value of x1 squared exists and it's finite. That's our assumption in here. And again, I could have written x2 or x3 in here. It doesn't matter. They all are supposed to follow the same distribution. So with this extra assumption, you get an analogous statement for these stronger notions of convergence. Specifically, if you take the sample averages, they are going to converge almost surely to the underlying expected value of the distribution. And yeah, you can also make a similar kind of statement regarding convergence in rth mean, where r is equal to 2. People would often refer to this as convergence in mean square, just terminology. So when r is equal to 2, you will get this convergence of the sample averages to the underlying expectation of the random variable. Intuitively, again, if you have very large samples, then you can say that the sample averages are going to be close to the expected value. All right, now yeah, let me see. Question. Is the second condition equivalent to saying that variance is finite for the random variable? And yeah, that's true, that's true. So this particular condition in here could have been rephrased by saying that we are assuming finite variance of this random variable. And yeah, that's because in any case, we are assuming here that the expected value exists and it's finite. So if this row moment exists and is finite, then you also have finite variance and vice versa. So that's a good observation. So this is definitely true. Great. So this is one law. I have one more law to kind of present here. Maybe I should go back to the visualization again here. So I started here actually with a standard normal distribution. So that would be a normal distribution that has mean 0 and that has standard deviation of 1. And then I consider different samples of different sample sizes. And then I would just evaluate the sample average for a particular draw. And yeah, you see that the sequence of the blue dots seems to be converging to 0 in here. All right, so the last theorem in here, the central limit theorem, that's a very important one. Yeah, let me go through the statement of the theorem. Then let's take a look at the visualization. And I will also need to discuss some intuitive implications of all of this. So I may need a little bit of time here still. Yeah, what's the statement of the central limit theorem? We are again going to have this kind of sequence, x1, x2, x3 of IID random variables. We are again going to make some assumptions. So specifically, we are going to assume that we have a finite expectation for this x1. And we are also going to assume that there is a finite variance. So non-zero variance that is finite and well-defined. So these are the assumptions. Then we will construct these sums. You can think of this as having a data set of size n and then computing the total the total of the different x's. That will be this Sn. That's our sequence. Of course, the sample average is going to be just this Sn divided by the little n, right? And the central limit theorem provides a statement about the shape of the distribution of Sn if you adjust it a little bit. So we are going to take Sn, we are going to shift it a bit, we are going to rescale it a bit. But once we are done with that, we will get actually a sequence of random variables that converges in distribution to the standard normal distribution that has mean 0 and a variance of 1. Now, what is this shift and the rescaling? So let's start slowly. This xn, that was a sum of the different x's, right? And each of the x's has some expected value. The expected value is mu, which means that the expected value of xn is going to be n times mu, right? N times mu shows up in here. So basically what we did on the left-hand side here, we subtracted the expected value of Sn from Sn itself. So right now, this kind of thing is going to have mean 0 or expected value of 0. And then, we would do something more in here. We would actually divide by the square root of n, and we would also divide by the standard deviation sigma. So that's done by considering this particular factor in here. So once you have this kind of a variable, you can think of it really as some shifted and rescaled version of the sample total. Once we have this variable, the claim is that it converges in distribution to the distribution of the standard normal. I have some visualization in here, but intuitively you can say that Sn roughly is going to behave like a normal distribution when n is large. Before I go to the visualization, any questions about the statement of this theorem? So it's actually a pretty crucial one, something that you may want to consider in many practical situations. And a lot of statistical tests are actually based on this kind of central limit theorem. And as for the visualization, I have it in here. But before that, let me see the questions. The question says, is the denominator that is rescaling the standard deviation of Sn? And you can think of it that way. That's a good observation. So if you actually compute the standard deviation of Sn, this is what we would be dividing by exactly. Great. As for the visualization, I want to show you how the kind of variables that we have here on the left-hand side, how they behave. That is, what would be their PDF? What would be their probability distribution function for a particular case that I want to consider? And specifically, let's start with a distribution that doesn't look like a normal distribution at all. I'm going to consider a distribution that's actually uniform, uniformly distributed, continuous random variable where we have some particular interval where it can land, and then outside of this interval we are going to have a 0 probability density. So the PDF of that underlying random variable can look something like what you see here. And what I plotted here is kind of the first member of this sequence. So here I have n equal to 1. That would be the PDF. Now, what if we change this? What if we change n to 2? This would be the PDF. This would be the PDF corresponding to n equal to 2. And again, it's the PDF of the random variable that you see right here. If you make n equal to 3, then Well, it's starting to look like normal distribution, right? It's not too far. N equal to 4, 5, 6, and so on. If you go to n equal to 10, it looks like a really nice normal distribution, doesn't it, right? So that's also one power of the central limit theorem. Even for relatively small sample sizes, you will already get here something that looks fairly close to the normal distribution. Maybe not exactly for the tails of the distribution, but at the middle, it looks actually pretty well like a normal distribution. It's actually a pretty important result in statistics that you would be using in many different cases. So that's the technical statement of this theorem. Any questions about this technical statement? If not, I also have some more intuitive discussion here. So how should you think about that? Well, the kind of random variable that we had in the theorem looks a little bit complicated, right? But let's not be completely rigorous. Let's just think intuitively. And let's think about approximate distributions for other random variables. Specifically, let's do some rescaling. So we take this variable that we had on the left-hand side, and let's rescale it a bit. Basically to replace this factor in front with 1 over n. This will bring us closer to sample averages. So if you do the rescaling, the mean is not going to change. The mean was 0, it remains 0. But the variance is going to change. If you correspondingly rescale a normal variable, then it will start following this other normal distribution, and that has a variance of sigma squared over n. Now let's make some more transformations here. It's kind of inconvenient that we see something subtracted on the left-hand side. So let's get rid of it. Let's consider, instead of this, the sample average, right? That would be Sn divided by n. And the sample average also can be written in terms of the individual observations in the sample xi. And what's the difference? Here we are just changing the mean, right? We shifted the mean by mu. And for that reason, this normal distribution is going to change to a normal distribution that has a different mean. What I'm doing here is I'm applying some transformations to the random variable that was supposed to be close to the standard normal distribution. And I'm making equivalent transformations also to a variable that literally follows that normal distribution. So the transform normal distribution is this one. It has mean mu, and it has this particular variance, sigma squared over n. And the intuitive statement would be that the sample mean for your observations is approximately going to follow this particular distribution. Now, I just say approximately, right? Because the statement of the central limit theorem was really a statement when n goes to infinity. And this particular distribution actually depends on little n, right? Its variance depends on little n. So it's not like a completely technical statement at this moment. But intuitively, you can think of it this way. You can say that the sample average approximately follows this distribution when n is large. And that's something that you may want to use as some approximation, maybe when you are designing some statistical test or something like that. All right, I think I covered what I wanted to cover today. Is there anything else? I think that's it. So if you have questions, I'm definitely happy to answer those questions. And I should also say that the next topic for us really should be hypothesis testing. It's pretty crucial to understand hypothesis testing. At the same time, hypothesis testing is just so confusing. So it could be some interesting discussion. Any more questions? Let me see. Yeah, question. Can you please add the proof of the center limit theorem later to the notes? For sure. So I can do that. In fact, there are lots of statements that I talk about, and if for any of them I did not provide a proof and you would like to see it, please let me know. I'm happy to include it in the notes. Great. Yeah, if there are no more questions, then we should close the session. Thanks a lot for joining, and the next time, yeah, let's get to hypothesis testing.